Today, I will give a presentation on gradient obfuscation gives a false sense of security in federated learning. This is a joint work with Dr. Richeng from Zhejiang University, Dr. Wong, Dr. Barron, and Dr. Dai from NC State University. So to begin with, I will first introduce the background of federated learning and talk about the threat model considered in our work. So in federated learning, clients with private data jointly solve a machine learning task. During the process, raw data are stored locally and will not be exchanged. For example, a server can broadcast global models to client, and client can train those models with its private data without transmitting private data to the server. And after that, the client can upload the local models back to the server. So one of the most popular protocols proposed by Google is known as federated averaging, which we present here in 4 steps. So in the first step, clients first download the global model from the server, and at this time point, everybody will have a same copy of the global model. And later, each client can update local models based on its own data. For example, they can use the gradient descent algorithm to update the model. And after that, clients can upload the model to the server. So it can either be the model parameters or accumulated gradients are computed over multiple local epochs. So on the server can take a linear combination of the models or gradients. And in this way, the server is able to update a global model. So this is one communication round between the server and client. And often this will be repeated for multiple times until the algorithm converges. After it converges, the server can deploy the model to clients. So one natural question we may raise for federated learning is, can privacy be leaked? Because we know our data never leaves the client. So usually, if the third party only receives the trained model or the gradients, it can only have a limited knowledge of the data distribution instead of how exactly the data looks like. So this was also the idea presented in the first paper by Google in the federated learning paper. So at that time, that's why the federated learning doesn't really need any crypto method to encrypt the message. Even for large models, it can be optimized in a pretty efficient way. However, studies have found that it is possible for an honest but curious server to reconstruct private data with the received gradients from clients. So in this work, we try to answer the question how realistic this threat model is under different obfuscation mechanisms. The obfuscation can come from multiple sources in practice. For example, if the client wants to save communication cost, it can apply gradient compression, or if the client wants to achieve more privacy, it can adopt differentially private training by injecting Gaussian noise. So we are going to answer the question, is the data leakage still happening under different obfuscation mechanisms? So next, I will present our framework to reconstruct image data from obfuscated gradients. So how can it happen for attacker to reconstruct the raw data from received gradients or received model weights? Let's consider a very simple neural network model, which takes 2 green nodes as inputs, and it has a hidden layer of 5 blue nodes. So essentially, the attacker wants to reconstruct 2 input green nodes, and at the same time, it has access to the gradients corresponds to those red edges in the first layer. So from the perspective of system of equations, the attacker knows 10 equations, and it tries to resolve 2 unknowns. This is an overdetermined system. So because we know the solution always exists, so the attacker is able to resolve this or reconstruct input with relatively low error. And let's see how a specific reconstruction attack can be performed. Again, on the client side, the client can first do the local computation based on its private data. For example, it can use gradient descent algorithm to calculate a gradient vector, or it can be based on multiple local iterations. And after that, it can apply a post-processing function to the gradient vector data. So the post-processing function, as I presented before, it can be gradient compression or differentially private mechanism. And later, this vector will be uploaded to the server. So prior work has proposed a scheme that, for example, can initialize a dummy data on the server side and feed it into the neural network. And later, they build an optimization problem to minimize the distance between the server dummy gradient and receive the gradient from the client. And by optimizing the dummy data, they're able to reconstruct some images that share similar patterns with the private data. However, this attack does not work for federated averaging, not along other schemes with obfuscations. So in our framework, we propose to introduce a pair of encoder and decoder. So the images will first be projected to a low-dimensional space, and later it will be mapped back to the image space. So normally, it has two benefits with the encoder-decoder design. So first, we can reduce number of unknowns. So it can accelerate optimization problem by restricting the search space dimensionality. And it also brings more flexibility to the design because you can use multiple tools for the encoder and decoder. For example, you can use a pre-trained GAN model or an autoencoder model. So we will initialize with a random vector in the low-dimensional space, and we will update it to let the dummy gradient to approximate the received gradient from client. And after the algorithm converges, we will decode this low-dimensional representation and use post-processing tools to obtain a set of images that look similar to the raw images. So next, I will present some case studies under different obfuscation schemes. So the first question we try to answer is, does gradient compression imply privacy? So first, we explore the quantization mechanism, which maps floating point number to 3-bit integers for the gradients. For both deterministic and randomized quantizer, our attacker is able to reconstruct images that look similar to the raw images. And we also explored gradient sparsification mechanism, which zeroes out smaller components in the gradients. And we found that the attacker is still able to reconstruct images with high qualities. So here we presented the quantitative result with so-called learned perceptual image patch similarity, which is our image quality measurement based on neural network model. So we explored an extreme case of binary quantization, the so-called sign SGD algorithm. So in sign SGD, each entry of the gradient is represented by either positive one or negative one. So this can be considered as one of the most aggressive quantization schemes. And we found out that our attacker is still able to reconstruct images that share the same structural information or semantics compared to raw images. So this tells us that gradient compression does not imply privacy, contrary to existing studies. And now let's switch the gear to the defender side. What if the client employ differentially private training? So does it enhance the privacy? So we found out that by improving the noise level in differential private training, in particular with Gaussian noise injection, the reconstruction quality indeed is decreased, especially when the noise level is high. However, we observed that the model test accuracy is also decreased significantly, and at the same time, the reconstruction does not totally fail. So indeed, the defender can achieve better privacy protection, but at the cost of the defender's model performance. So based on this observation, we're able to examine the utility privacy trade-offs for more defense schemes in federated learning. So here in this figure, the horizontal axis is a privacy protection level, which we use the data reconstruction quality as a proxy of the privacy indicator. And for the vertical axis, we use the model test accuracy as a proxy for the utility. So from the defender perspective, the defender may want to achieve some cross points on the top left corner, which means the defense can achieve both high utility and high privacy protection level. And this is also consistent with prior works that our existing defense is able to achieve our high accuracy and high privacy protection level because prior attack does not have a capability to reconstruct images from this defense. However, our attack is able to reconstruct images with high quality. And we evaluate existing defenses on our attack mechanism, and we find that under all of the defenses, we're able to reconstruct images to a certain extent. So in summary, we're able to improve the attack efficiency by pushing the achievable utility privacy region from the top left corner to the bottom right corner. And it suggests that existing defenses in federated learning may give us a false sense of security. So we also propose a variant that can reconstruct images at a semantic level, especially when the reconstruction is not clear enough. So for example, under the sign SGD case or differentially private case, the reconstruction sometimes you don't see the full object in the reconstructed images. So we propose this variant to further enhance the quality. So for example, in this figure, we let the attacker to search in the GAN latent space, and the attacker is able to reconstruct images that have the same semantics. Like in this scenario, a dog standing on top of grass, and our attacker is able to reconstruct 3 different realizations that share the same semantics with the raw image. And for the second set of image, the raw image is our post box in the snow, and our attacker is also able to reconstruct different realizations that share the same semantics. So we encourage you to read our papers for more details. So to conclude, we have studied privacy leakage problem under different obfuscation mechanisms in federated learning. And we propose a more general attack framework, which shows that gradient compression or the noisy gradient in differential privacy does not provide perfect privacy protection. And in the future, it will be interesting to explore hybrid defense and to give a more precise privacy notion, especially under this data reconstruction attack context. So thank you for your attention. Thank you.